Can you see the slides?
Yes, we can.
Okay, cool. Awesome. So yes, hello again. Today I'm going to be presenting the GLEAM 4Jansky sample, which is a compilation of nearly 2,000 of the brightest radio sources in the southern sky. But I'm going to start with a very general introduction to radio astronomy to benefit especially the students joining us today. And then I'll follow this with some context for the area of research that I concentrate on, which is active galactic nuclei. And this will then be followed by introducing the GLEAM 4Jansky sample, which is actually selected at low radio frequencies, but I'll also present some new Meerkat observations and give you a few examples of radio sources that are showing spectral curvature in their emission. So they're not following the usual power law function, which is what we assume to be describing the total emission from these sources. So to start off, we're familiar with looking up at the night sky and seeing all these specks of light, which tend to be stars in our own galaxy, maybe even planets, or some of the brightest galaxies, so extragalactic sources. But the problem is that we have a large amount of dust also getting in the way. And so if we only do our astronomy at optical wavelengths, we're going to have an incomplete view or picture of the universe. And this is most apparent if we were to look up at the Milky Way. We can see these large dust lanes obscuring the light.
We have some tea actually, yeah.
Oh, sorry.
Okay, some lemons.
Would people like to mute if they're not going to ask a question? That's okay. So you have these dust lanes that are obscuring the light from these galaxies. This is most apparent for the Milky Way, but you can imagine, especially at high redshift, that we could have systems that have so much dust that no light is able to reach our optical telescopes at all. And so this is where it becomes really important to look at the night sky, the sky in general, at multiple wavelengths. And the advantage of radio astronomy is it is able to see through this dust and giving us a more complete picture of the night sky. So just to illustrate this, this is a very nice diagram of the transparency of the atmosphere according to different wavelengths, different types of radiation, going through from gamma radiation all the way through to radio radiation. And so the type of astronomy we're most familiar with is done in this very narrow band around 10 to the minus 6. These are all numbers in units of meters, by the way. And we do most of our astronomy here, but we can obviously feel the heat from the sun in the infrared, but we're going to concentrate on this very nice wide window at radio wavelengths. And it's this nice wide window that allows us to do multiple radio frequency observations, reaching the telescopes that we have here on the ground on Earth. So we'll start off with the longer radio wavelengths, which is just another way of saying we're going to concentrate on the lower radio frequencies to start with. The picture at the top is the low frequency radio telescope in the Northern Hemisphere, known as LOFAR. And this is actually distributed across multiple countries over Europe, but this particular photo is from the station in Sweden. And at the bottom, we have the low frequency telescope in the Southern Hemisphere, which is the Murchison Widefield array located in the Western Australian desert. And this is the work that we used for conducting our investigations of the GLEAM 4Jansky sample. Now, I'd like to also highlight that the Murchison Widefield array is located in the same place where the low frequency component of the square kilometer array will be. So this is a protected radio quiet zone. And so we have very little radio pollution, basically, from civilizations, mobile phones, televisions, etc., that would otherwise interfere with the science that we want to do. This is known as radio frequency interference. We want to get away from that as much as possible. Now, I thought I'd use this very nice instrument that's available online. Unfortunately, I'm not going to do a live demo, but do look up GLEAMoscope, because it's a very nice outreach tool that allows you to pan across the different parts of the sky. And then, as you can see in the top right, we have this way of scrolling between different wavelengths. And so you can look at the same patch of sky at different wavelengths and see how much it has changed. So if we focus maybe on this particularly bright optical source here in the middle, we can see as we go into the radio regime, we actually have these very powerful radio jets being emitted. And this source at the center is known as Centaurus A. We see these very nice large lobes, and just comparing again, flicking between the optical and radio, we're picking up a lot more extragalactic sources, or these point-like dots, but also seeing much more, many more extended structures. And if we focus on, I don't know if you can see my cursor, but let's, there you go. Focus on one particular radio galaxy, which is just there. So this is a source that me and my collaborators tend to refer to as the TIE Fighter. So maybe fans of Star Wars will appreciate why. And this is kind of the poster child for the GLEAM-4Jansky sample. So I'll show it again later in the talk. But what we have here is a galaxy that has a supermassive black hole, which is accreting material and producing a large amount of emission, and these large jets being ejected from that host galaxy. So what do I actually mean by active galactic nucleus? So again, we're talking about a particular type of galaxy that has a supermassive black hole at the center, and it's accreting material. So there's gas falling close to the black hole and generating this accretion disk. And some of the emission is produced in the radio band, but there's also a large amount of accretion-related emission at other wavelengths too. Just to point out that not all active galaxies produce these powerful radio jets as indicated here, but the ones that do are of course much brighter in the radio and therefore easier to detect and therefore much better studied than their radio quiet AGN counterparts. So what exactly are these radio jets and how do they form? That's a great question, if I do say so myself. The idea is that we have this accretion disk of plasma that's formed around the black hole. So this is gas from different directions falling in. You're cancelling out that angular momentum and you're forming this accretion, this whirlpool. The idea is that that accretion disk has a lot of magnetic field strength that is kind of twisting up those magnetic field lines, but maybe also the spin of the black hole at the center is also contributing and causing these field lines to almost create kind of a tunnel that constricts the high energy plasma and ejects it out along these collimated field lines. So it's still unclear exactly how do we go from what's approximately chaotic accretion into these very well-ordered structures. So that's still an area of much research. Next, we want to understand, well, how do these jets interact with their environment and their surroundings? And this is where it becomes really interesting to observe the same source at multiple frequencies and therefore different radio resolutions. But also for that, you might need to use completely different radio telescopes altogether. And so this is M87, so also known as Virgo A. And on, oops, sorry. How do I go back? Oh, it won't let me go back. Can I stop sharing and?
Your numbers in the bottom corner.
Yes, thanks. Yep, the zoom controls is not helping. Sorry. So on the left-hand side, we have the radio emission from LOFAR for this source, and you can see it nicely maps out the much more extended structure associated with this radio galaxy. But at higher frequencies, we get better resolution, and so we can kind of zoom in on the radio emission. And if we use particularly extended radio telescopes over several thousand kilometer baselines, we can make use of very large, very long interferometry instead. So this is VLBI telescopes. And at the bottom, we can see, you may be familiar with this image from the Event Horizon Telescope, which came out last year, which was the very first image of an accretion disk surrounding a supermassive black hole. So now I'm just going to give you one slide summary of why we are interested in studying active galaxies in terms of their role in galaxy evolution. So it's been observed that both star formation and black hole accretion appear to follow similar trajectories over cosmic time, as shown in the top left corner. And these two processes are believed to be critical for how galaxies form and evolve. Now, is this similar history due to there being genuine interactions between these two feedback processes? Or is it simply due to there being a common reservoir of gas that fuels both the star formation and black hole accretion? And similarly, there's debate over the overall impact of radio jets on the surroundings. And so we're going to concentrate on the plot in the lower left. These are radio contours from a nearby AGN. And that radio jet is impacting on an otherwise stable molecular cloud, which is shown by this grayscale. And that interaction of the jet impacting on that molecular cloud is actually triggering its collapse and subsequent star formation. But at the same time, we have examples in other systems where a jet might impact upon a cloud and completely cause the gas to completely disperse, in which case you're preventing stars from forming. So there's that debate over the overall impact of those radio jets. And then on the right, we note that there's a very similar, almost a co-evolution thought to exist between the supermassive black hole, its black hole mass, and the velocity dispersion of the bulge. And this is seen for a wide variety of galaxy types and over a very wide range in black hole masses. So again, we want to know, are these due to genuine feedback mechanisms or just a coincidence connected with the amount of gas that is available in the system? And when you think you've seen everything, then Meerkat, being the amazing radio telescope that it is, shows you something new. And this is a very bright radio galaxy. It is above 4 Jansky, and yet it's making us rethink, do we really know everything there is to know about even these brightest radio sources? This is don't know why it's gone to the next slide. This is a Meerkat image that has been completely reduced using an automated pipeline known as Caracal. And that allows you to also make additional tweaks depending on what science case you have. So you can take this pipeline, you can run it in automated settings, see how far you get, and then do your adjustments as necessary. What's really incredible with this image is that not only do we pick out the beautiful kind of filamentary structure in the lobes and get an idea of the entangled magnetic field lines there, but we also have these brand new threads here. So we've called them collimated synchrotron threads. And we still don't understand what exactly is causing them or why they are there. Is it just that they're being energized by electrons that have actually been energized in the lobes, and they're feeding along these magnetic field lines that are already present. The picture is very unclear. And the question that this might raise is, do all really bright radio galaxies show these threads? And if so, how common are they? So of course, a very good place to start would be to take a complete sample of all the brightest radio sources in the southern sky. Before we get there just yet, I want to emphasize why it's important to select our sample at low radio frequencies. And this is because there are many radio data sets out there, but we want to obviously use the data set that gives us the best starting point. So at low frequencies, we have radio emission that's typically coming from the lobes of the radio galaxy, so it has this steep spectral shape. Whereas at higher frequencies, we tend to be dominated by radio emission connected with the accretion disk, the core emission. And the thing is that if we do our selection at this higher frequency, then we start to encounter a bias towards core-dominated sources. And this is the result of something known as Doppler boosting. It affects hotspots, radio jets, and cores by artificially boosting the measured flux density, because anything that is oriented slightly towards the line of sight has its flux density increased, whereas a radio jet that's slightly pointed away from us is Doppler deboosted instead. So by selecting at lower frequencies, we actually completely avoid this bias that's introduced by Doppler boosting, also known as relativistic beaming. And as a reminder, it was Bartel that used a low frequency source sample, the famous 3CRR sample, to test the unification idea that radio galaxies and radio loud quasars are in fact the same type of object, they're just oriented differently with respect to the line of sight. So in addition to allowing us to create a complete sample that doesn't have this orientation bias, low frequency observations also give us much better constraints of the radio spectrum, which I'll show some examples of later. But since radio emission moves to lower energies as it ages, it means we also can pick up a much older population of these sources. And in doing so, we can have a better appreciation of the timescales involved in AGN activity and also how it is interacting with the surrounding environment. And for this work, we make use of the Murchison Widefield array, which, as I mentioned before, is located in the Western Australian desert. And the data that we've used for this particular project came from the phase 1 configuration. And this had a maximum baseline of 3 kilometers, which gave us a typical resolution of around 2 arc minutes at 200 megahertz. Now that's not great resolution, I know, but the key strength of the Murchison Widefield array is its excellent spectral coverage. And this again comes down to it being in this radio quiet zone where we have very little radio frequency interference and therefore excellent spectral coverage for doing our science. This telescope was used to observe the entire southern sky at low frequencies, and this is the survey known as GLEAM. And the extragalactic catalogue became publicly available back in 2017. And for around 300,000 components, so individual detections on the sky, we have 20 flux density measurements spanning a frequency range of 70 to 230 megahertz. And we're interested in the very brightest of those detections. So really it's kind of skimming off the brightest components in the GLEAM catalogue and collecting that information together because we're interested in the sources, not just individual detections. And it's those brighter sources, brighter than 4 Jansky at 151 megahertz, that we refer to as the GLEAM-4-Jansky sample. And here on the left is a histogram of their radio brightness. And we can see to the right of the vertical dashed line are the types of sources that we already kind of know about, thanks to the famous Cambridge sample 3CRR. And like that sample, the vast majority of these bright radio sources are active galaxies with very powerful radio jets. But we have a sample that is over 10 times larger than 3CRR, which means that we can both study the properties of these objects more robustly as a function of redshift, and also as a function of environment. We want to understand what impact does the environment have in the properties that we observe. So a large part of the work done for the GLEAM-4-Jansky sample was repeated visual inspection because of the low resolution that we get with the MWA. It became quickly apparent that we need to gather as much information as possible from other radio surveys. And here are just a couple of examples. So in red are the GLEAM contours at 200 megahertz. And we also overlay contours from TGSS, which is using the GMRT in India. That's at 150 megahertz, but it completely resolves out the extended emission that the MWA is sensitive to. You can see how much more extended those red contours are compared to the yellow contours. And then for the sources that are above -40 in declination, we can make use of NVSS. Those are the blue contours. But below that declination limit, we instead use SUMS, which is at 843 megahertz instead. And it's through this visual inspection that we can collapse what is basically a list of individual detections in the GLEAM catalog into a list of sources. Sorry, I shouldn't have gone just yet. And we find that about 74% of this sample, so this is about 2,000 objects, are still compact even at the higher resolution. And on the right-hand side, this particular radio galaxy is the same one I showed earlier when we were using the gleamoscope, in which I called the TIE Fighter. This radio galaxy is so large, it's about 30 arc minutes from lobe to lobe. And it's described by 4 individual detections in the GLEAM catalog. But we sum all of that emission to give us our total flux densities in the GLEAM-4-Jansky catalog instead. And this particular source is also detected in the Australia Telescope 20 gigahertz survey, which nicely marks the core for this radio galaxy. So as mentioned, we're feeding in a load of information in creating the GLEAM-4-Jansky catalog. Of course, we start with the GLEAM catalog and its images. We feed in the information from other radio surveys, but also mid-infrared information from Allwise and optical information from the 6-degree field galaxy survey. And it's through multiple passes of inspection that we can identify sources that were poorly fit, maybe by AGN, which is the source finder used for making the GLEAM catalog, and also identify sources that need to be recentroided. And by that, we use the information in NVSS and SUMS to calculate where is the brightness weighted centroid for the source, which gives us a better indication of where the host galaxy is likely to be. We're just trying to narrow down our search radius, basically. So when we inspect these sources, we need to determine the morphology, but also the host galaxy hand in hand. They go together doing that. Sorry, there must be some timer that started on the slides. And the full description of this catalog can be found in paper 1 of the GLEAM-4-Jansky, describing the GLEAM-4-Jansky sample. But all of these additional literature checks that we do is basically what makes up the entirety of paper 2. There's a lot of work that's gone into this because, well, the there are higher resolution radio images out there, but not in a consistent, well, they don't provide consistent coverage across the entire southern sky. So in that case, it can be quite bitty, and we have to do these additional checks to make sure that we haven't been misled maybe by some of the radio surveys at lower resolution. And also just quite complicated morphologies, that's also the issue, where you think you might have obviously a host galaxy in the middle, but if the radio source is very asymmetric, you're going to be completely wrong. So we want to make sure that we've definitely got that host galaxy correct, because that's really the pinpoint upon which we do all of our cross-matching in order to feed in information at other wavelengths. So as part of the value-added GLEAM-4Jansky catalog, we provide those summed flux densities at low frequencies, also information at around 1 gigahertz, and 4 sets of spectral indices given the different radio surveys that we use. I'm pleased to say that about 86% of the GLEAM-4Jansky sources have been identified in the mid-infrared, and we're doing some follow-up work to make sure we get that identification completeness to 100% if we want to do comparisons to simulations, for example. We need to make sure the entire sample is complete for that. And here are just a few examples of more unusual radio sources in the GLEAM-4Jansky sample. Because we are observing the entire southern sky, we can pick up rare sources such as these much more easily. So on the left, we have an S or Z-shaped source, which I'll come back to on the next slide. In the middle, we have the famous X-shaped source, which I'll talk about towards the end of this presentation. And on the right-hand side, we have examples of bent tail radio galaxies. So in the top right, we have a wide-angled tailed radio galaxy. And in the bottom right, we have a narrow-angled tailed radio galaxy. The idea here is that we have our typical radio galaxy that has ejected radio jets in opposite directions, but the motion of that radio galaxy as it's passing through the medium causes those jets to become bent backwards, and we have this tail of emission. And so it'd be quite interesting to use this subset of bent tail galaxies in a flux limited sample to investigate, for example, cluster properties, the motion of the galaxies, but also using them as a probe for the surrounding medium. So a bit more detail onto this unusual S or Z-shaped source. So it comes down to the idea that we have this supermassive black hole at the center that appears to be, that could be precessing. So much like a spinning top as shown in the top right. So you'd have your radio jets, again, coming in opposite directions, but that spinning, that precession is causing those radio jets to kind of carve out this nice helical structure, as shown in the bottom right, this kind of corkscrew effect. And if you imagine just blanking out the fainter emission in the bottom right, you can kind of see how you would get this S or Z-shaped pattern. And this image in the bottom right is actually an X-ray binary or micro-quasar known as SS433. So it'd be quite cool to see how prominent, how common these kind of sources are, and maybe get an idea of the physical parameters associated with supermassive black holes in these systems. So there are many aspects we want to look at further, and to start with, we're going to make use of the world's best radio telescope, which we're very lucky is situated here in South Africa. This is in the Karoo. It's made up of 64 dishes, which are about 13 meters across. And what's really great is that we can get simultaneously really good UV coverage with both short baselines and long baselines, and so build up our picture of these radio sources in a more complete fashion without having to use multiple telescopes and combining them together. So what we did for our open time proposal was to point Meerkat at 140 of the GLEAM 4Jansky sources. And for this, we just spent 5 minutes per source. They're so bright that we don't really need to spend any longer than that on them. But the sources we picked out were the ones where the existing radio images are just too poor resolution to understand what is going on, what is the exact morphology, but more critically, where is the host galaxy for that radio emission? Now we need to know that exact galaxy if we want to bring in a multi-wavelength perspective of these sources and cross-match information at different wavelengths. So again, here we have just an example of clearly a double radio galaxy, but the possible candidates in the mid-infrared image, there's too many to know, well, which one is the correct one. So we want to have a more sensitive image also to pick out the location of the core and therefore identify the host galaxy correctly. And just point out that even though these are so bright, these sources, there's still a lot we don't know about them. And as shown by the histogram here, we're talking about sources that are from 4 Janskys all the way up to 50 Janskys. But it's just that the existing information over the southern sky is quite bitty. And so we're trying to do this in a cohesive manner as much as possible. So to start off with, I just want to point out that even though they are really bright at 151 megahertz, that doesn't mean that they're going to be really bright at around 1 gigahertz, relevant for Meerkat. And this is just one particular source where, so the TGS image is shown on the bottom left. You can see it's quite blurry. This is only 25 arc second resolution. But with Meerkat, we can go down to 10 arc seconds. This crispens up the image. We can see it's clearly an edge brightened radio galaxy. But with this very first pass, there's still no real indication of where the radio core may be. So this is something we have to watch out for. But not all is lost, because this was just a first pass. And since then, the imaging and calibration steps that we've applied for the Meerkat data, our open time data set, is much improved. And I'd like to illustrate this with a few more sources now. So here we have, in the top left, this is clearly a bent tail radio galaxy, but it's in a dense environment where there are many mid-infrared sources, and it's unclear which is the correct host. In the middle, we have what looks to be a head-tail galaxy. So if you can see, if you're close enough, you can see the magenta diamond, which marks an optically bright source. So that is likely to be the host galaxy in this case. And on the right, again, another example of a radio source in a dense field. So where exactly is the host for this radio emission? So what does Meerkat show us? Quite a difference. It's been very satisfying to look at these images kind of come to life. I've spent 4 years of my life looking at blobs, so I'm very happy to see them in their true form using Meerkat. And on the bottom left, with this much better resolution, we can even make out the location of the core, so unequivocally identify the host galaxy for this radio emission. In the middle, we can see the peak brightness towards the top, indeed appearing to coincide with that optically bright source. But there's 2 tails of emission, radio emission, as they move downwards subtly. They then appear to pool together again. We have this clump of plasma towards the bottom. And you've got this very unusual hollow then that exists between the two narrow tails. And just looking at this to start with, I've called this the paperclip. Not very imaginative, but let me know if you've got a better name for this one. And then on the right, you think that Meerkat's going to help you, but we just get a sharper image of something that we still can't make sense of. Instead, we've got almost like a three-legged monster happening in this field. So this is where it would be really nice to get a spectral index map to hopefully use the spectral information to identify the flat radio emission that we expect to be associated with the core, and use that to then identify the host galaxy for this source. Oops, nope. Yeah. And just to point out that, or to remind you that each of these sources, we've only observed them for 5 minutes, but Meerkat is just so amazing and has this beautiful large field of view that there's a whole bunch of other sources nearby, and it's very easy to get distracted from your science topic, which is at the pointing center, because you've got all these amazing sources in the surroundings. So my particular favorite that I've come across so far, at least, is this one in the top right, where you can clearly make out the direction of the radio jets, but then after it's kind of exhausted itself by interacting with the surrounding medium, you have the energized plasma that is kind of trailing off in the background, creating this really beautiful morphology. And then just to also hammer home that it's the sensitivity of Meerkat that allows us to pick up even these really wispy radio lobes, as shown in the bottom left and the bottom right of this slide. So this is giving us a much better appreciation of just how many extended radio galaxies there are out there, much more than we appreciated before. And by having a more complete sample, we can then also understand better how does that active galaxy interact with the surrounding mediums, and over what timescales as well, because it could be that at the higher frequencies, whoops, oh, sorry, the timer again, is only picking out that emission associated with the core, but the wispy lobes was a previous epoch of activity. But then if you happen to have a spare 10 hours on Meerkats and a particularly extended source that you'd like to look at, this is the kind of image that you can expect to get. So this is the same X-shaped source I showed earlier. And the idea here is that we have the supermassive black hole at the center. It's ejected its radio jets along that approximately north-south direction, interacted with the medium. It's energized all this plasma. This plasma is then flowing back towards the center. But at the center of the galaxy, we also have a large gas reservoir. And this is more dense than the backflow plasma. And so that causes the plasma to become deflected, and basically following the path of least resistance, creating this very nice X-shaped pattern. And this is going against the alternative explanation for these X-shaped sources, which is that the supermassive black hole is switching on in one particular direction and then precessing in the same way as shown earlier with the S or Z-shaped source. It switched off, precessed into a different orientation, and switched on again, producing a second pair of radio jets. So those are kind of the two competing ideas for these X-shaped sources. But it's the level of detail that we get with Meerkat that we can clearly see this, the beautiful flow of material within the lobes as it's, whoops, as it goes closer, or it flows back towards the center and then gets deflected again, and giving us these two nice boomerang shapes, as shown, illustrated in the top left. So yes, little preview there. I'm very excited to see what Meerkat shows for other GLEAM-4Jansky sources. This is just to highlight that they are propping up in lots of different data sets. So we have already an open time proposal that was to look at X-shaped sources in particular. Some of these sources are at northerly enough declinations that they actually overlap with the 3C and 4C surveys. So there are people looking at those objects as well. And of course, many of these coincide with the cluster legacy survey. So do keep a lookout for them. I would just be excited just to see the new images again, having seen blobs for the past few years. So yeah, if you have anything interesting to show me, like, feel free to get in touch. I'd be very happy to see. So another aspect that we would like to investigate further in terms of science to do with radio jets and active galactic nuclei is exactly how do they interact with the surrounding H1 gas. And I believe many studies tend to be on an individual, like, source by source basis. And this is one particular source shown at the top, which is a 4C source. In gray is the CO emission, or in emission at the systemic velocity. And then if you look around a velocity of -1,000, that's associated with the outflow of this source. And then overlaid on that is an absorption profile, which has actually been inverted. So the strongest emission, the strongest absorption is this tall orange peak. And then we also have much broader absorption associated with the southern lobe of this radio galaxy. And what would be cool is to look at this in a statistical manner using the GLEAM-4Jansky sources, but at redshifts that are close enough that we could also pick up hopefully H1 emission using Meerkat. So I'm still collecting redshift information for the whole sample, but I can already say that we have at least 78 sources that are at low redshift enough to do this kind of work. So if you know anyone interested in this interaction between radio jets and H1 gas, please do tell them to get in touch with myself. And now I'd like to also demonstrate that we have another subset of the sources where we've extended that excellent spectral coverage from GLEAM all the way up to 20 gigahertz. And that is using additional measurements from the Australia Telescope Compact Array. And that allows us to get measurements at about 5, 9, and 20 gigahertz. And as you can see, we don't have Jansky sources just following the standard power law, which is what we always assume when we want to extrapolate a radio flux density at a different frequency. We find within this this subset of sources, we also have these peak spectrum sources. So at lower frequencies, those low frequency photons are being absorbed. It's either free absorption or synchrotron self-absorption that's taking place there. And those sources tend to be young radio galaxies. There's also a subset within this subset that have this kind of concave radio spectrum. And from first inspection, just first investigation, the majority of these appear to be blazars. So this is the case where we're actually looking down the barrel of the radio jet. And so there's a large degree of variability as well we have to be aware of in terms of radio flux density measurements. And then in the bottom right, we have some particularly unusual cases where we see a kink actually in the radio spectrum. Now, this could be just simply due to the poor resolution of the MWA, that you've actually got two completely separate radio sources that are just blended together by the MWA beam. But if we find that genuinely it is a single radio source that's producing this emission, then it could be that each component of that spectrum is actually due to an individual epoch of AGN activity. And those two epochs have then just been superimposed on one another. So that requires further investigation. But note that if we didn't have the contiguous coverage from GLEAM, we wouldn't have picked up that kink at all. So another reason why we have radio spectra showing this curved structure is due to spectral aging. And on the top, we have examples of spectral age models and associated chi-squared and error. And the bottom is the corresponding power spectrum, basically, or radio, the energy associated with those electrons. Unfortunately, these two authors have used their rainbow in the opposite direction. So in the bottom, we actually have the youngest radio spectrum being in blue and the oldest radio spectrum being in red. And so we start off with this usual power law function representing new or a continual injection of electrons. And then but over time, if there isn't that continuous injection of electrons, those higher energy photons become depleted. So we have energy losses through synchrotron radiation or inverse Compton scattering or simple adiabatic expansion. And those losses of photons means you're going to have a spectrum that takes on a more and more curved appearance over time. So we can use multiple radio frequency measurements to calculate the typical age of that radio emission. And another thing we can look out for within the GLEAM-4Jansky sample are restarted radio galaxies. And the idea here is that we have old relic radio lobes associated with a previous epoch of activity, but more recently, for some reason, there's maybe more gas that's falling on to the supermassive black holes at the center, reigniting the accretion there and creating more new emission at higher frequencies, which is most evident for the core. And here is just one particular extended radio galaxy. I believe it's 1 megaparsecs across, so a giant radio galaxy. And it's so large that it's actually resolved into individual components in GLEAM. And that means we can use the excellent coverage from the MWA to probe each of those components separately. We can see the northern and the southern lobe represented by these blue and red data points, and they show our typical steep spectral emission. Whereas the radio emission associated with the core, it's the only one to actually be detected at 20 gigahertz at higher frequencies. And that follows our standard flat spectral emission that we expect to see. And it's by summing each of those components that we see this total radio emission represented by the black data points. So it's steep at low frequencies, but it then flattens out as we go to higher frequencies. And that means we could even use that spectral signature to pick out radio galaxies for follow-up and investigate whether they truly are restarted AGN. So this is my summary slide now. On the top left is actually a plot that will be shown in the next GLEAM-4Jansky paper. And it takes the spectral index at low frequencies and compares it to the spectral index towards higher frequencies. Now, if those two spectral indices are the same, then we would expect the source just to lie along this dashed line here, in which case it's our usual behavior of a power law being used to describe the total radio emission. But the deviation away from that dashed line gives us an idea of the degree of spectral curvature for the GLEAM-4Jansky sources in this sample. And on the right is just to hammer home this point that at higher frequencies, like around 1 gigahertz, we're actually probing more recent or ongoing AGN activity, but it's only by going to lower frequencies that we see the cumulative effect and the buildup of past epochs of activity instead. And by comparing those two regimes, we can then determine the duty cycle of the AGN. In other words, how much of its time does it spend in an on state compared to how much time it spends in an off state instead. In the bottom right is a histogram of all the R-band magnitudes found so far for the GLEAM-4Jansky sample. I'm very pleased to say that we're hoping to go down to an optical completeness of around 20 in R-band magnitude using follow-up spectroscopy using the Southern African Large Telescope. And the really, really bright sources there, they're just going to be observed hopefully in P4 time. So where the observing conditions aren't so good, but these are optically bright sources anyway, so we can hopefully knock them off quite quickly. I'm also delighted to say that papers 1 and 2 are finally complete and they're publicly available, and the catalogue is also on Visia, as well as the GitHub repository, which I've put at the bottom of this slide. We have follow-up at higher frequencies, around 10 gigahertz using the Australia Telescope Compact Array, and 140 sources to be inspected by my master's student who's starting soon using new images from Meerkat. Thank you very much for listening.
Thanks a lot, Sarah. Let me just let's see. Okay. Does anyone have any questions? You maybe just give.
Just ask first. Does anyone else?
Yeah. Anyone else? Do you have any questions?
I've got one. Just with regards to your 5 minutes pointings with Meerkat. What sort of effect did you have on your UV coverage, but also your PSF with such short integration times?
Well, that's a good question, but I haven't actually seen the PSF. This is admittedly like work done by Ian Hayward.
Okay.
But yeah, I would imagine it would still be quite, or depending on the declination, how elliptical the beam would be.
Okay, just because the snapshots that you showed still look, I mean, the sources, the compact sources still looked quite good. Often with short integration times, you get sort of weird artifacts because you have gaps, severe gaps in your UV coverage. So yeah,
I mean, he's been looking carefully at the dynamic range because we were worried about that for such short scans.
Okay.
But yeah, I'm not sure the detail or how that's varied with declination. Actually, we've tried not to go further than declination of +10, just to be on the safe side.
Okay. And then was the 5 minutes contiguous, or were they sort of split up across RA? Do you know?
No, they had to be 5 minutes all in one go, because the huge problem for this project was the slew time, because these sources, they're distributed all over the sky. So there's a massive overhead just to get to the right position. So these are actually done using self-cal. We tried to do using the cross-cal technique to start with, which is when we got this kind of image, but there were problems with flagging and all sorts. But these are self-cal images with bespoke masking as well. So yeah, a lot of manual tweaks to make sure you're distinguishing between artifacts and what is real but complicated morphology. So
are those details in one of the papers already published, or?
No, so the the papers already published is just the GLEAM work really, and the visual inspection and mid-infrared information. This is going to be a new paper to fill in the gaps, because we don't have the mid-infrared identifications for these sources yet.
Okay, great, thanks.
Nice.
Does anyone else? Okay.
Yeah, I type a Q in the chat, but
Oh, I can't see the chat. Maybe if I stop sharing, I don't know.
Okay. I guess the chair was wondering. Okay, fine. Yeah, okay. Sorry. Thanks for the interesting talk. And I was interested in actually one of the slides in the introduction part, which is fairly early on, which is about the center mass of the black hole and the velocity dispersion of the bulge.
Oh yeah.
Yeah, I mean, whenever I saw it, I saw this many years ago, and I feel very interesting and strange, because the black hole is very compact and sitting in the very center of the galaxy, whereas the bulge is, a few kiloparsec, which is much larger scale. So the scale doesn't really match at all. How come the dynamic motion of the star in the bulge would know such a compact, massive black hole in a kind of black hole in the middle? It's just the scale just doesn't really match, and but they have a perfect correlation in between. So is there any deeper understanding of this for these recent years?
Well, the usual explanation is that even though they are on very different spatial scales, we still have radio jets that can go up to 1 megaparsec scales, so way beyond the bulge anyway, way beyond the host galaxy. So the idea is that you have this kinetic but also thermal feedback from the AGN that could be influencing the host galaxy. And I'm actually more in favor of the thermal feedback, because not all AGN produce radio jets. You have a large amount of emission being created just thermally through the accretion disk. And if you have heating of the surrounding medium, you're going to prevent stars from forming, and that will impact the stellar mass, and then you impact the velocity dispersion of the bulge. So that's where I lean towards, because you also have examples of study sources where the radio jets are actually too powerful and they puncture a hole, and then their impact is kind of so far away, it doesn't have that much feedback in terms of the host galaxy it even came from. So there's competing work, and this is why it's still a hot area of debate.
Yeah, just by your interesting reasoning, can you explain this proportionality behavior? Like the higher black hole mass would be that the perhaps more heating will going on, and how does that impact? How does that make the velocity dispersion become larger? I'm just trying to understand this. Yeah. Mm-hmm.
So there's there's another plot I removed from this talk because we're running out of time in the introduction. But there's some work was modeling from quite a while ago by Croton et al. So this is comparing galaxy luminosity functions from models to observations. And the idea is that in the most massive systems, those are the ones that tend also to have a lot of this kinetic feedback from the AGN. And if you have the feedback dispersing or heating up the surrounding medium, you're going to prevent stars forming. So it's kind of, I don't want to say self-fulfilling prophecy, but self-regulation. That's what it's termed as. So that's at the high mass end. But the low mass end, you also have feedback through supernovae explosions as well. So there's two areas of feedback. It's not just AGN.
And those feedback happen on the scale of the bulge, a few kiloparsec, perhaps. Okay.
Well, that's the difficulty. How do we get that spatial information connected with the feedback? So that's where you want to use X-ray observations look at where is the energy being deposited in the surroundings.
Okay, thank you. Yeah.
Nice.
Hi, I had a question. So you've got all these weird and wacky shaped sources. Is anyone doing any like simulations of those, and has anyone managed to reproduce anything at all what looks like that on a computer or not?
Gosh, yeah, that's a really good question. I mean, the simulations I have seen so far are just struggling to predict the fraction of F2 galaxies, because there's the underlying debate is nature versus nurture. Is it, are they intrinsically more powerful, or is it the surrounding medium that's influencing the morphology much more? Right. So if we can understand that basic morphology classification, which has existed since 1974, then we can do the next step, which is the more complicated S and Z shaped objects. But yeah, you'd also need, I guess, simulations of the gas distribution, not just the radio jets.
MHD, presumably, I guess.
Mm-hmm.
Like, yeah. It seems like it should be, these images should be a powerful motivating factor for someone somewhere to
I hope so.
See what's going on with these.
Yeah, okay. But the other issue is that in the GLEAM-4Jansky papers, the morphology that we report is still limited by our images, which is at best 25 arcsecond. So there's still a lot of apparently compact sources that could actually be more S-shaped sources and more X-shaped sources, but at the moment we just don't know. I don't want to wish anyone to have to do bespoke masking for 2,000 sources. So this is an option. I've thought, oh, we should just put all of them, just observe all of them with Meerkat. But I know that that's a very involved job. So I'd prefer people to like take parts and work on that. If they want to observe the whole lot, then do get in touch. But just as long as you know what you're letting yourself in for, because there's a lot of manual labor going on into reducing the data.
Okay.